Let's continue. A path in a network. In the previous slides, we gave some definitions about flow in a network and the capacity of edges. And we have seen that there is an upper bound for the maximum flow in any network. Now we focus on finding a flow of maximum value in any given network. How do you assign flows? Let's define the path first. Now this path definition is different than what we have defined as path in general networks. A path in a network is a sequence of distinct vertices. It can be shown as Q, a series of vertices V0, V1 up to Vk, and it starts from source X and it ends at sink Y, which means V0 is equal to X, Vk is equal to Y, and Q is a path in the underlying graph of N. This means that we will disregard the direction of edges. For any two consecutive vertices, Vi and Vi plus 1, here on this path, Vi plus 1 may be an edge, or Vi plus 1 Vi may be an edge. Remember, network edges are directed. This means we can traverse an edge in either direction. We will just disregard the directions. If the direction of the edges is followed, then this edge will be called a forward edge. If we cross an edge on the opposite direction, then we will call this edge a reverse edge. Remember, we're talking about a path Q. Now let's define the augmenting path. An augmenting path in a given for a given flow is a path Q such that each edge on this path obeys these two rules, either one of these two rules. The first one says, if this is a forward edge, then the difference between the capacity and the flow on this edge must be positive. This means that if we are following a forward edge, there should be some positive unused capacity. If it is a reverse edge, then we are only looking at the value of the flow on this edge, and that value should be a positive value. It should not be 0. The path Q is an augmenting path if the path is an augmenting path, then we will define delta as follows. Delta will be chosen as the minimum value of all these delta I values over all edges along the path Q. Delta is the minimum value of all delta I values. Now this might seem a bit complicated, but it will be much more clear if we examine this example. So here is our same example. And here is an example path. X, 1, 2, 3, Y. Now on this path you can see that some of the edges are forward edge, like X to 1 is a forward edge. And some of the edges are a reverse edge, 1 to 2. Now we are taking the path from X to 1 to 2 to 3 to Y. You can see that I am traversing some of the edges on the opposite direction, and these are reverse edges. Reverse edges are 2, 1 and 3, 2. and forward edges are x1 and 3y. So our path is again x1, 2, 3y. The forward edges are x1 and 3y. The reverse edges are 1, 2, 2, 3. And if you go back to the delta value definitions, a delta in the forward edge is the difference between the capacity and the flow. So here, delta is equal to 1. In the reverse edge, delta is only the flow value. We don't take the capacity of the edge into consideration. So delta here is again equal to 1. In this edge here, delta is equal to 1 because of flow value is equal to 1. And finally, in this edge, 3 to y, the delta value is equal to 2. That's the difference between the capacity and the flow. So the minimum of all these delta values is equal to 1. Now, once we have augmenting path, then we will look now what augmenting a flow means. For each edge of the path, an augmenting path, for which delta I is equal to delta, that is the minimum value of all deltas, is called a bottleneck edge relative to flow and path Q. For a given network and flow Fn, so again, we have two different elements here. We have the basic network with the capacities, and then we have flow on each edge, flow values on each edge. Given these two different set of information, if the augmenting path, if any augmenting path Q exists, then we can construct a new flow F prime n. And the value of F prime n is equal to the value of the previous flow plus the delta value. Now, how do we augment the flow? Augmenting basically means increasing the flow. We will add delta along an augmenting path. This addition will preserve the conservation of flow requirements at each vertex except the source and the sink. The net flow from X is increased by the addition of delta to the flow along X V1, the first edge of Q. So here is our same example. If we continue on this example, remember that this was our augmenting path. The delta value was equal to 1. Now the bottleneck edges are all these three edges here except 3 to y. Delta is equal to 1. Now how do we augment the flow in general? We will assign the flow value of 2 to edge x1 here. Because I can increase the flow by 1 here up to the capacity. If I increase the value by 1, my flow value here will be equal to 2. Similarly, I can increase the flow from 1 to 2, 0, which means since this is a reverse edge, the flow was equal to 1. This is actually not contributing to the flow. It is a negative value. It affects the flow negatively. So I'm going to decrease this value to 0 by 1, which means it will contribute for me to augment this value. 2 to 3, this edge, again, it's a reverse edge. So again, we assign 0 here by decreasing this flow value. This is a reverse flow. And then finally, the last edge, 3 to y, we augment the flow by 1. Again, the delta value. So resulting flow on this edge will be equal to 2. This idea of augmenting paths forms a basis for an algorithm. That algorithm is by Ford-Fulkerson. It starts from an initial flow, say F0. This could be a zero flow, which means we can have only zero values all over the network for all edges. And we can still augment the flow step by step to reach the maximum flow. By starting with F0, we construct a sequence of flows F1, F2, until we reach a maximum value. So along the sequence, Fi plus n is constructed from Fi by finding an augmenting path. Termination of such an algorithm is guaranteed because every time we find an augmenting path, we are guaranteed that the next flow, Fi plus 1, will be greater than the previous flow value. If no augmenting path exists, then Fin is the maximum flow.